All right, good morning. I'm a little bit surprised that we managed to fill up more than half of the hall. I'm guessing that most of you are from the East Coast and have managed to get up in the morning. For those of you who are from the West Coast, I deeply appreciate you getting up and listening to what I have to say about LLMs. Now, I think if you think about what happened in the last couple of years, there are two things that I can think of that have greatly changed everyone's lives. The first one, of course, was the last years of the pandemic. I don't know how many of you have lost loved ones or felt like those years were wasted staying at home. But one of the things that happened during those years was actually the quiet revolution that was happening in LLMs. And what I wanted to address today to you specifically was the way in which this technology came about. Why did we go from chatbots and then thinking about tool use? And then finally, the realization that these aren't just language models, but the fact that they really ended up having planning and reasoning capabilities that are really quite incredible, that I believe will have great implications in our lives. So with that, a little bit of a history to start out the talk. I wanted to kind of take us back a little bit, perhaps maybe even to the beginning of my personal career a little bit. Some of you know that I started my career at Xerox PARC, and this is a machine that I don't know how many of you at this point actually have spent time actually looking at the history of computing. But when you think about the fact that the real revolution of many of us who started this career early, the first revolution was the personal computing, right? And even though many of the ideas behind LLMs, for example, these days, how many of us are fighting for GPU or TPU chips in our workplaces? This is batch computing's come back at this point, right? But back in the days, the concept that you could have essentially what was thought of at the time, a supercomputer underneath your desk, was completely revolutionary. And this was a version of it, in fact, introduced to the world in 1973. And many years later, I had the great pleasure of actually going and working at Xerox PARC, and that was the reason why I went there, was this was the place that invented the revolution. And this is me, back in those days, much younger version of myself, in front of my computer there. And again, the idea at the time, you can imagine, was to push the boundary of what computing can do. So I have 5 displays on my desk and a coding keyboard, all kinds of crazy things that I was experimenting with. And it was that experimental method and that spirit that brought us to the web. And I don't know how many of you needed coffee this morning in order to stay awake for this talk, but just 15 minutes ago, I ran upstairs to get my coffee. And what's interesting about that is, of course, many of you at this point don't remember this, but in the beginning of the web revolution, if you wanted to use a search engine, you had a search engine called Xarchie. How many, I don't know if I can actually see you, but how many of you remember Xarchie? This is just going to date you a little bit. I see literally maybe about 10 hands maximum. That's kind of sad. But Xarchie was actually a live crawler. So the idea was you would put in keywords, and it's very important that you get capitalization correct and no misspellings whatsoever, because it's literally a match of the file name on FTP servers all around the world. So you would input your keyword, and then you would go get a cup of coffee, and you would hope to God that when you get back, that you actually found the file and you didn't mistype a single character, because if you did, you would have to start over and get another cup of coffee. The good news was that there were a lot of graduate students that were very awake in the laboratory, because they were just always searching for the files that were available. But still, it was faster than actually going across the mall to the library, because you could literally just do it right there with a cup of coffee and can find the file that you needed. But of course, also in 1991 was the invention of the web browser. And then very soon after that, we ended up with Google. And instantaneously, it wasn't coffee. It was seconds before you get information. And this was amazing to all of us, of course, but terrible for the coffee stand owners, because they now have much reduced revenue as a result of this. But of course, Google, merely 7 or 8 years later, didn't stop there. We ended up actually building things like, for example, indexing the entire world's book as much as it was possible, and making it searchable and accessible to everyone. Now, these revolutions proceeded another 8 years later with the introduction of the mobile phone. And that happened with the iPhone and, of course, Android, both at the same time in the same year. And the mobile revolution was also interesting in the following sense, that the coffee makers, the coffee stand owners, at this point were very, very happy, because everyone could still do their Google searches, but they just carried their phone to the coffee stand. So the revenue came back merely 8 years later. And at this point, in fact, some economies are completely run on mobile phones. It's completely mobile first, right? In China, you wouldn't introduce Bard or ChatGPT on the desktop first, as we did here in America. You would have introduced it on the mobile phone first, because that is where everybody is. Now, you might then think that 8 years later, from 2007, that we would be due for a revolution. So that would roughly be about 2015 or so. And the reality in 2015 or so was what we were working on, everyone was working on, was deep neural networks. Now, it seemed like that there was going to be a revolution as a result of deep learning. So think about this. This was what was happening, that you could take out your phone, take a picture of something, like a lion, hopefully behind bars or something like that, so you're safe. And then it would literally recognize it and say that it's a lion, right? Now, what was even more incredible was that you could be in a noisy bar, and you could say something like, how cold is it outside? Should I wear my jacket? Or something like that. And it would deal with all that noise and actually recognize the thing that you said, that speech to text were so good by 2016 or so that it became commonplace. And for many of us who started with the mobile revolution in 2007, this was incredible, right? Because the expectation before neural network, was that voice recognition definitely do not work. Like, 20% of the time it was going to fail. But it worked. And in fact, it worked so well that we now expect it to work, and when it doesn't, we're pretty upset, right? And then, of course, beyond that, the statistical machine translation revolution continued as well. So you could put in text in English, like, hello, how are you? And ask it to translate into French, and it would say, bonjour, comment allez-vous? And this was incredible, because at first, it just seemed like it was able to translate these simple phrases, but soon after, you could put in very complicated text. In fact, I think it was maybe about 2015 or so that I was just talking to one of the executive meeting organizers for this conference, and we were talking about going to Korea and Germany, for example. One year, I think it may have been in 2014, I went to a German HCI conference. It was completely conducted entirely in German, and the proceedings were also in German. Although I have taken 4 years of German in high school, I have pretty much given it all back to my German teacher, unfortunately. I could just barely hold a conversation to find where the restroom is at this point. And what was so incredible about the statistical machine translation capabilities that Google and other companies offer was I literally just cut and pasted the entire papers into the translation machine and was able to read most of it. And I raised my hand and asked my question in English, and they were all amazed that my German was so good. But when in fact I was completely augmented by a statistical machine translation capability. What was probably the thing that really surprised me in 2016 or so was actually this capability, which is that you put in an image into the system and ask it to caption that image, and it would actually generate free-form text that described what were the most salient features in the image. So here's an example where it says it's a blue and yellow train traveling down the tracks. That was incredible because there was no direction given to the system about what exactly it should describe, but yet it generated token by token, essentially, what was in the image. And of course, people started thinking about all the various different implications of this, which, as an example, for those of us who are hard of vision, now you might be able to use your phone to better navigate the city or recognize objects that you might want to interact with. A very common use case of object recognition in this case is actually the recognition of coins or how much to actually pay your coffee vendor, right? So you can see that I keep going back to coffee because I got coffee on my mind. But one of the things that is really interesting about this slide, actually, is these last two items at the bottom. How many of us in 2016, even though we all recognize that these capabilities were there, actually realized that the generative AI moment was going to be upon us merely 6 years later? Right? I would contend in 2016, 2015 or so, you can see that 8-year cycle was what we were on. In 2016, when I was thinking about these problems, I did not realize that the generative AI moment was going to be here. But if you looked at that very last function as an example of this, right? The fact that you can put in an image and have it generate token by token, a caption that was reasonably accurate about what was in the image, that foretold essentially all the things that we're about to see today. And I did not recognize that pattern. If I did, I'd probably be a billionaire at this point. And all of you would have been, because I think many of you were watching this revolution actually unfold in front of your eyes and didn't realize that was happening. Now, of course, many times when people hear the word revolution, they always think it's got to be a hyperbole. But one of the things that I experience as someone who's I was just talking about this with somebody else, I forget who it was, about the revolution that happened in Taiwan in terms of democracy. And the interesting thing about revolutions is that oftentimes they unfold in front of your eyes quietly until the moment it really hits you. And this is an example of that. So in 2011, if you put in a object recognition task into the machine, just by uploading an image, for example, the machine error was roughly around 26%. And the human performance was about 5%. This is what's interesting is by 2016, actually, machines' accuracy for object recognition was already at 3%. In other words, this is superhuman performance. Right? So not only was in 2016, if you had been paying attention, you would have realized that the seed of the generative AI moment was upon us. And you would have realized that superhuman performance might be possible. You would have been surprised at that moment, but many of us were still asleep when this was happening. Now, when you think back on those times in 2016, what did you feel like was the thing that changed? And the answer was, about this was really interesting because in the 1980s, no one took neural networks seriously, right? And we all know this story at this point, including the Turing Award winners just a few years ago, who are celebrated for their ability to continue to stay the course with neural networks and its research. But between 1980 and now, what happened was more compute and more data. And what makes this interesting, of course, was the fact that KDD is the conference that really paid attention to data. So one of the things that I find interesting, having been part of this community for a number of years at this point, was we've seen the rise of machine learning conferences. I've been to exactly this convention center merely, I think, 5 or 6 years ago for NeurIPS. And boy, there was like thousands and thousands of people that were here. And of course, all of them were working on methods, right? Methods for machine learning. And it was because of more compute that they were all excited about the neural network revolution, right? But the reality in 2016 was, how did deep learning actually change people's lives? Yes, okay, your phone can recognize your voice so you can call mom more easily at the bar. And maybe you could recognize bills or fruits or something better at a grocery store, but like how many of us needed to pull out a phone to recognize some fruit that you've never had before? Unless you're traveling in Asia, I guess you don't really need that kind of capability. So like when you think about the revolution of the mobile phone, where like half of the traffic went from the desktop onto the mobile phone, that's the kind of level of revolution that we're talking about. But the degree in which deep learning were actually changing people's lives, or I would contend actually was fairly minimal in 2016. So the revolution that we were expecting every 8 years didn't really happen. So I think we missed actually a generation. And so I was thinking, like, what was going to happen? Like, it seemed like deep learning was upon us, but yet my life didn't change. And I think this is the moment that our lives are about to change. So now, not just more compute and more data, and KDD has stayed the course, and 2,000 of you apparently registered for the conference. This is great, and you're all here in Long Beach. And I think of all the people who are going to lose their jobs, the people who understand data are not going to lose their jobs. And so that's good news for all of you who pay attention to data. Give yourself a hand, I guess. All right, so what makes this interesting, of course, I kind of alluded this, is that the fact that all of us have gotten comfortable with the fact that these revolutions were coming every 8 years, and comfortable about the fact these things were changing our lives. If you think about the fact that as humans, we couldn't fly 100 years ago, okay? But yet, my flight to Long Beach was delayed by half an hour, and I was really annoyed. How many of you had a delayed flight coming into LA or Long Beach? Yeah, I mean, like there's at least about 10% of the hands went up there. So 100 years ago, we couldn't fly, and then 100 years later, we're annoyed when our flights are delayed by 30 minutes. This is how our expectation have been changing over time. And the famous science fiction writer, Arthur C. Clarke, once said, any sufficient advanced technology is not different from magic. I love this quote because to some extent, we're all getting used to the fact that our mobile phone just understands us when we speak to it at this point. And yet, the interesting thing is, we have gotten used to it merely 8 years later. Right? Any common technology is not magic. So at this moment, LLM feels like magic to you. But 8 years from now, you'll feel that it's completely commonplace. This is what is amazing about these quiet revolutions. Now, at this point, what I like to do is give you a little bit of a taste for what it was like to kind of live through this quiet revolution, starting roughly around the time when LLMs were really starting to be developed seriously at Google and other companies. So the first place where people wanted to apply LLMs was, of course, with chatbots and personal assistants. Now, how we got here was really a set of very seminal research work that was happening in the machine learning conferences. In particular, in 2014, there was this piece of work on sequence-to-sequence learning with neural networks. And this was a deeply influential paper done by my colleague who's now in my team, Clarke, and other people at Google. And merely 6 months after, there was people looking at this piece of work. And back then, by the way, they were all built with sequential neural networks like LSTMs, et cetera, were already thinking about how we could use these sequence-to-sequence models for a conversational model. And conversation was the first thing that everyone thought of. And then a few years later, of course, the famous attention paper was published. And that formed the conceptual network that was necessary for many of the new advances to come. Lambda was then demoed at Google I/O in 2021. Again, some of us took notice, but didn't necessarily thought this was, it's a cute chatbot. I chat with humans all the time. Why do I need to chat with a machine, right? So, it sounded interesting, but, maybe not for all of us. And then what was interesting was actually the publication of chain of thought papers, and that started some of the work that we have been doing in my team on reasoning, which we'll talk about in a little bit later in the talk. And then continue scaling and realization of the zero-shot capabilities of these language models, which again, I'm going to get into a bit more detail on later in the talk. Now, one of the key concepts that's happening in this space, of course, was the fact that many of us were guilty of this, is that we have this tendency to want to build separate neural models for everything. That was the way that my team, for example, that was working on recommendations and ads ranking systems, were building these systems. And we would have one model, in fact, for the click-through prediction, and we would have another model for conversion and auction. And then we would have another model for predicting human behavior in some other setting, right? And these models were proliferating throughout the entire company. And we hired a lot of engineers in order to build these different models. What was going on in the language model space instead was that we could build a single model that could do machine translation as well as even text-to-speech. We already could tell that you could merge all these models into a single model. And this enabled the concept that of the multitude of tasks that these language models will be able to do, and kind of foretold the possibility that that was going to happen. So I mentioned this paper, Lambda, that we published. And at that point already, the parameter size was up to 137 billion parameters. This was published in, if I remember correctly, in the early parts of 2021. And at that point, we realized in order to control this technology, and by control, I mean trying to get it to align with human values and trying to get it to behave the way we want it to behave, we fine-tuned these models for sensibility, specificity, interestingness, and dealing with safety, factuality issues, as well as we were already thinking about how does tool augmentation, retrieval augmentation, were going to improve the quality of these models. And it really foreshadowed the development of Bard and some of the other technology that we ended up working on at Google. So speaking about Google, right, all of you, hopefully at this point, Google has done a good job of keep telling this to people. And I think this is actually a good thing to do because this aligns the entire company and its mission. That what we're trying to do is organize world's information and making it universally accessible and useful. So very early on, when I started helping to manage the Lambda team, was to think about how this LLM technology was going to change Google's mission. And our thinking was that what we could do is to organize world's information with large language models, and then making it universally accessible and useful through natural conversations. Again, as I mentioned, with the sequence-to-sequence paper, and then very soon after, when you saw the beginnings of something that looked like it was going to maybe fully solve, quote unquote, the Turing test, it seemed like the dream of having a personal assistant for all of us was right around the corner. And of course, this dream of having a personal assistant for all of us came from the fact that most of us can't afford $100,000 to hire a personal assistant, right? Like it's just, that's the luxury of the rich. But imagine how humankind could be augmented if all of us had personal assistant. Now, the interesting thing about this is, don't forget, I mentioned that the technology seems to suggest not only are we able to build human-like capabilities, but that they may be superhuman. And this is really quite something to keep in mind of.
Hey Google, how are you?
I'm doing pretty great. Thanks for asking. Any plans today?
I'm planning on going to the beach today.
Surf's up.
How's the weather?
Currently in Alameda, it's 61 degrees and partly cloudy.
So I just played this audio clip to give you a sense of exactly what the current experience working with an assistant feels like. I don't know how you feel about it, but it feels very transactional. Short, courteous, nice answers, but it didn't feel like if I hired a butler or I had a concierge here at the hotel that interacted with me in this following manner, I probably would be like, this person is a little bit cold. I'm not getting my $100,000 worth, right, of the service that I'm expecting. So I think all of us are expecting something a lot more natural, and that the information will be a lot more proactive, as well as the assistance will be a little bit more proactive. Maybe it would go something like this.
Hey Google, how are you?
I'm doing pretty great. Thanks for asking. Any plans today?
Yeah, I'm thinking of going to the beach in about an hour.
Sounds fun, but if you're going to Half Moon Bay again, expect some rain.
Oh no, can you remind me to bring my rain gear?
Sure, I'll remind you at 9:25.
Perfect, thanks.
No problem. I'm sure you'll have a great time at the beach, rain or shine.
What this example illustrates, I think it's interesting because some of you know that I came originally from information visualization and then working on HCI issues, particularly system issues in HCI. One of the things that we talked about in that field quite a bit was mixed initiative. The fact that it wasn't just the machine completely being, transactional and having a servitude kind of attitude to serving you as an assistant, but it will proactively ask you how you're doing, be a bit more empathetic. But also, when you say, I'm thinking about going to the beach in about an hour, it knows about the time right now, and it will proactively offer to remind you at 9:25, right? This is the kind of personal assistant that we're really hoping for. Of course, in the future, you all will be hoping that it will also be a robot that's embodied in the real life and would actually go to the coffee stand and order you a coffee and bring it back, right? But the fact that this is mixed initiative and the conversation felt a lot more natural, the way that you would expect a personal assistant to be like, is the future that we were hoping for at that moment in time when we started thinking about the fact that these LLMs can carry on a very natural conversation. So merely a few years later, we started building Bard. And hopefully, all of you had a chance to try Bard. But as an example of the kind of assistance that you can get from this LLM is, let's say, for example, you had a yearly goal of reading 20 books. That's a pretty tall order, by the way. I don't know how many of you are able to consume a book every couple of weeks. You ask it to brainstorm some ways to plan a strategy for actually reading 20 books a year. And it will come up with a list of strategies that you might be able to carry out in order to get there. So one of the things that we realized that was different from just the natural conversation was the fact that these large language models are actually capable of doing some planning This was really surprising to us because it felt like maybe it was going to be a Eliza kind of cute chatbot thing that was going to like mechanical Turk a conversation, if you will, right? Like maybe it will be a cute chatbot that you talk to late at night when you're bored, but not something that was going to help you plan your life, or maybe even a vacation, or how to read 20 books. Another example that someone from our team wanted to try was fly fishing, wanted to introduce their kids to the fly fishing sport. And it's like, this is a difficult sport to introduce your kids to. What are the strategies for doing that? And just casually put in a prompt about getting some ideas about how to introduce my daughter to fly fishing. And Bard gave some ideas that he was really happy with. So this is interesting because we started to realize that these LLMs weren't just cute, natural conversation partners, but the fact that they can actually solve problems for you, truly like the way that you would expect a personal assistant to actually do. Then we also realized something else that was really interesting about machine translation. And I love this example because I mentioned I had taken 4 years of German in high school, and I had remembered this phrase, which was, Ich verstehe nur Bahnhof. And if you translate that directly into English, how many German speakers in the audience today, by the way? I hope you appreciate this example. But if you translate that into English, it literally means I only understand train stations. And it makes no sense as English speakers, right? But as an idiom in German, because train stations in Germany is extremely loud. The trains are coming and going, people are walking by, maybe buying coffee, right? And they're having conversation at the top of their lungs. You can just imagine a couple at the train station with like 2 kids that are running around and they're trying to go to, I don't know, Hamburg or something like that. And maybe the wife is yelling at the husband, and the husband would say, I only understand train stations. What they really mean is, this is so loud in here, I can't understand anything that you're saying. This is an idiom in German, right? Now, if you had put this into Google Translate, it may have actually very faithfully translated into, I only understand train stations. But if you ask Bard to explain, what does that mean? It will actually explain to you the cultural significance of this, right? Like, by the way, yes, this translation can be misunderstood because the German phrase, ich verstehe nur Bahnhof, is an idiom that means I don't understand anything. It can be misinterpreted as meaning I only understand train stations, right? So what was going on here is that the LLM actually encodes the cultural meanings, the semantics of these phrases. Now, of course, you would imagine that there's an idiom dictionary somewhere, and you could have put in the entire phrase as it is, and it would retrieve that entry and give you the answer. That's a retrieval-based approach to solving these problems. And merely 10 years ago, that's how we would have solved the problem for people, right? But now, with LLMs, it could understand even variations of this phrase without an exact match, because it understands the cultural significance of that particular phrase. Now, what was perhaps even more surprising to me was the fact that these LLMs could do coding. I don't know how many of you have been surprised by this over the last year or two, but if you ask it to explain, for example, what JAX is, it will explain by a generative AI, like token by token, it would generate an explanation what JAX is as a framework for building neural networks. Or if you say, I believe this code has a bug in it, please fix the bug and add line-by-line comments in Korean. I don't know how often you need to write code comments in Korean, but Bard can do it. This is mind-blowing, right? Like that you can give this level of instruction and have the machine at least get it. In fact, I would contend, even if it gets it half right, you'd have been pretty happy. And the fact that they can do this token by token was truly something that I did not expect. Now, all these LLMs, underneath it is essentially powered by 3 recipes. And at this point, actually, the method that's required to build these systems is, I would say, almost commoditized. The 3 recipes are pre-training model, where you want to have a base model of sufficient size that is being trained on a sufficiently good corpus on the order of billions or many more billions of examples and tokens. And then you would fine-tune it, particularly using instruction fine-tuning, on tens and thousands, maybe 100,000, maybe at most 1 million examples that are specialized in specific tasks. And then once you do that, the model essentially has been imbued with some zero-shot capabilities. And by zero-shot, this means that it's able to perform new tasks. Like, for example, instead of saying, I wanted to read 20 books, if you said, I want to read 20 books about golf, or how to make milkshakes, any topic that you wanted, right? It would come up with the answer, because it's capable of doing zero-shot performance. And then finally, there's all these things that we could do on prompting. And this, by the way, there's still a lot of mystery that's going on with prompting, because there have been some really interesting paper over the last year about how micro changes in the prompt can get the model very different levels of accuracy performance. And so we're still discovering what's going on here. But I think if you talk to your significant others, you might understand the concept of micro changes to your prompting. Because even adding a teeny little word like please and thank you gets you very different results from your significant others. So I highly encourage you to also do some prompt tuning engineering work with your significant others. I have personally experienced this, unfortunately. One of the things that's going on with these 3 recipes was that very soon, in the last 2 years, we have already realized that it was not enough. Why was it not enough? In fact, for those of you who played with ChatGPT, you would have recognized this already. If you ask about today's weather, for example, it would say, I'm sorry, but my data was trained up to, I forget what it was, December 2021 or something like that, and I just don't know the answer to that question, right? The reality is that if you wanted to know about what's going on today or what the weather is, you need instantaneous access to some new information source that's not in the pre-trained model, that's not in the fine-tuning examples, but you needed, well, frankly, Google, right? You needed to Google what is the latest weather, or you need a weather app, right? That gives you that information. So what was going on was the following, that we realized that Bard by itself, without this retrieval augmentation, would often get things wrong. A good example of some of the things that we were seeing that were getting wrong was even questions like, how do I take care of a plant? It would sometimes hallucinate an answer. That wasn't quite right. It would get the name of the plant wrong, or it would get the instruction just slightly wrong. So, if you're killing a plant, I suppose that's not necessarily that big of a problem. But if you give instructions for something else, like fixing a faucet or something like that, and you give the wrong instruction, you might end up with a flood in your kitchen. Right? So, figuring this out and dealing with hallucination was one of the things that we were very worried about in the early days of development of LLMs. So one of the things that we realized was that leveraging external knowledge was especially important. The way this worked was if you had a prompt, a query that goes into an LLM, we had a triggering module that would decide whether this particular prompt required the consultation of external knowledge. And you might have now started to realize that there's a theme also kind of chaining the train of thought, if you will, in my talk, which is how do we make use of search engines and external knowledge sources to augment our capabilities. And so knowing when to go to Google for information is one of the key things that we have all learned, right? Like, oh, I don't know that, and so I got to figure out what is the exact correct query term to put into Google to get the answer that I need. So one of the things that we have been training Google to do is actually understanding your queries, and query understanding is big business. But also, don't forget, we have been trained by Google on how to use Google, right? We know how to formulate queries the way that, in a way Google expects. This is one of the interesting things about the HCI, the interaction between search engines and humans. And now we're teaching an LLM how to do query formulation, how to use these external tools. So once the query has been formed, it goes out and retrieves the information and comes back. And it now needs to read all that information just the way that we do. An LLM will have to read all the web snippets in order to decide what is the correct piece of information to piece together to answer a question. So for example, how to take care of a plant, or how to fix a faucet, or what today's weather is. Right? If you get conflicting information, which one is the more authoritative source to use is another example of the kind of skill that an LLM will have to learn. So how do you get the LLM to learn that, by the way? It's through fine-tuning. So you give it fine-tuning examples so that it knows, for example, that Wikipedia is a more reliable source than some random website out there. So it will have to recognize URLs, for example, and say, oh, I should trust the Wikipedia web snippet more than some other web snippets. But if Wikipedia is not there, what are these other websites I should trust? So all these, in a way, are things that we would need to teach a beginning web user, right? So think about your kids who are learning how to use the web. If you let them use Google, I don't know what age kids these days start to use Google. You also teach them about how to use it, how to integrate the information that they're getting from the search result page, and then they would try and pull out the answer. And that's essentially what we're trying to get our LLMs to do. What makes retrieval augmentation for LLMs really interesting is that by having this kind of external memory to guide the generation process, it leverages both parametric and non-parametric knowledge. And by that I mean the non-parametric part is, of course, what has been compressed into the LLM, right? And all the information that has been brought in from the external source at this point are chunked into pieces and then can be looked up and integrated into the final answer. This is what's really amazing about retrieval augmentation, is that we still don't understand the degree in which we need the information to be already pre-existing in the pre-trained model, and how much of it we should rely on external knowledge sources. And there's, in my opinion, still a raging debate about the size of the raw model, the base model that we need in order for it to have some basic reasoning capabilities, summarization capabilities, so that you can use these external knowledge sources, information retrieval systems, in a productive manner. And figuring that out will, of course, help us figure out how much serving capacity and how much machines to buy, for example. So knowing the answer to this might also help you decide how much to invest in certain stocks, if you get my drift. Of course, textual search engines is not the only thing that you can consult in tool use. You could also imagine consulting image retrieval services, because a query generation could generate a query to an image search engine. So, example, that you might be planning for a trip to New Orleans. Many times, these larger conferences at this point is also held in New Orleans, because they have a really large convention center there as well. And so if you put in a prompt like, what are some must-see sites in New Orleans, Bard would actually generate not just an answer, a list, which would be pretty boring to look through, and you're going to have to do even more Google searches. By the way, this is not a ploy to get you to do more Google searches, right? But we would actually go out and issue all these image queries for you and bring those sites and the images directly into the answer so that you would get both the textual answer and an example of what you would see if you actually went to New Orleans. Right? So this kind of integration of a multimodal experience now starts to feel much like how the personal concierge service would perform for you. Like this now actually feels less transactional and very helpful and very proactive in offering advice and things that you could do when you're going on a vacation. Other things that we thought about in multimodality, I'm a dog lover. And so you could see that if you wanted to, maybe make a card with your dog, and you say, hey, here's a nice picture of my dog. And then you put it into Bard and say, can you write a funny caption? And it will come up with a funny caption. I think in the future, there should be a button here that says, write a funny caption, and then send it out to Walmart or Walgreens or whatever. And I want a card in my mail tomorrow, right, with this funny caption in it. And then you just need to sign your card and you're done. As an example of a kind of personal butler service that we might all desire at some point. I think this would make Valentine's Day a lot easier for a certain segment of our audience going forward. So this kind of multimodality capability where you can have image input and image output, and of course, as you can imagine, you will end up also with audio input and audio output and all kinds of senses and perception, things that we already had talked about in that first part of the deep learning revolution. That is all going to be integrated into the large foundation model revolution that we're experiencing. And coming soon will be other tool use augmentation and app integration. You would just say, I need an Uber, or I'm going to have a hot pot dinner on Thursday. Order me the necessary ingredients, and it would call out to a grocery app and just have everything show up at your doorstep. Just the way that you would imagine a personal assistant would do for you. What I wanted to emphasize here is to take a slight pause and think about what is truly happening here. I hope you all agree that as humans, we have been augmented by search engines in the following way. If someone asked you, why is the sky blue, and you didn't know the answer, you knew to pick up your phone, the mobile revolution. Use Google, type in, why is the sky blue? You read the answer and give that answer back to your daughter. It required 2 revolutions in our lifetime for that to happen. The mobile revolution that I talked about, and the search engine revolution that happened merely 8 years before that. Those 2 things together made us superhumans. We were one version of human before 2007, and we're another version of human with a mobile phone in our hands. And we became superhuman. Now, the same thing happened to LLMs. LLMs plus search engine became super LLM. You see where I'm going with this? Now, if we take humans and we add super LLM to it, we become super humans. I think that's pretty incredible. And the superhuman part of this is actually the key piece that I have not talked about yet. And I think this is what underlies the entire revolution, and that's reasoning. If you think about having been to many of these machine learning conferences in the last couple of years, how the difference between human intelligence and machine learning truly were. And I have to hat tip to my colleague Danny Zhao. And by the way, he's going to be giving a keynote in the LLM Day later, and I'll have the information for you in a second, for starting a lot of this reasoning research with me in the Brainstar group merely a few years ago. He's the one who really have been in conversation with me and thinking about these nuanced differences between humans and machine learning. Humans learn from very few examples. You just need to give them some examples of how to do something, and they're capable of generalizing from that. They're able to explain their prediction, but yet our recommendation systems are terrible at explaining their prediction. And they have this really strong out-of-distribution generalization capability that machine learning systems in general just couldn't do. And there were all these papers over the last decade about how to fill this gap. And Danny and I would both contend that they have all failed at this point, right? Like, they don't fulfill the premise that we were talking about here, that they learned from only a few examples, that they explained their predictions, or that they had strong generalization capabilities. They just don't. On the other hand, our kids have very strong generalization capabilities, sometimes to our children. Right? It's like, how did you generalize from that example to this other example? So the hypothesis that Danny and I had was, how do we improve reasoning of LLMs? Can we teach these machines like how we teach kids? That was the genesis of the chain of thought paper that we published nearly a few months later. In the standard few-shot prompting, the pattern was you put in an input and an output, just the way that you would expect how the machine learning system would be built, because that was the paradigm that we were built on. But chain of thought prompting, on the other hand, was you put an input, as well as you still get an output, but in the middle, you would put in an explanation how the input got transformed using a template or a schemata into the output. So let me give you an example. If Roger had 5 tennis balls, he buys 2 more cans, and each can has 3 tennis balls. How many balls does he have now? And the answer is 11. So that would be a few-shot prompting. You gave an input, you gave an example and an output, and then you now actually test it. At inference time, you give it a new example. The cafeteria has 23 apples. They used 20 of them to make lunch, and they bought 6 more. How many apples do they have now? If you tried Bard at one point in time, it would have said the answer is 27. And that's wrong. But if you insert this explanation that's in blue on the right-hand side here, which says, Roger started with 5 balls. 2 cans of 3 tennis ball cans is 6 balls. So altogether, 5 plus 6 is 11. So the answer is 11. Right? So it actually goes through the steps of answering the question. And then all of a sudden, you put in this example just by prompting, and you ask the model the same question that we had asked earlier, it would get the answer right. It would say 23 apples originally, minus 20 would have been 3 apples left. They bought 6 more, so 3 plus 6 is 9. So the answer is 9 and not 27. When we saw this result, I was flabbergasted. That merely a little bit of a change in the prompting get completely different answer. Notice the technique that I used here again was the foreshadowing. As it turns out, adding please and thank you don't always work, but apparently asking it to think step by step and giving it as an example of how to think step by step, you actually get much better answers out of LLMs. This was completely surprising to many of us. It turns out that if you test this on many different tasks, you could actually get pretty good performance. You could ask it to understand dates, sports. You could get it to plan out a robot to move around in a room. You could get it to do program tasks, even reason about coin flips and tracking the state. Lots of different things that you wanted the model to do. It started to be able to perform them, not with flawless accuracy, but much better than where we were before. And as an example of applying this was we tried these techniques on a set of tasks called Big Bench Hard. And on the left-hand side was the performance of the model before chain of thought prompting. On the right-hand side is the performance of the model after chain of thought prompting. You can see the entire distribution just literally shifted. This was the surprising part about the work that we did in this area. The other thing that was interesting was that when we teach our kids, we often ask them to, can you think about it in a different way? And so one of the ideas that our coworker, Xuezhi Wang, decided to work on was the idea that if you just ask the model multiple times to perform the task, and you ask it to, with different temperature, it would go through different reasoning path, decoding path, that would give you slightly different answers. But if you tallied up all the various different reasoning paths and how many times it gave the same answer, which will be in green here, the red one would be the wrong answer, that if you took a majority vote, if more reasoning path led to the same answer, and you use that as a clue as to what the correct answer is, you also get a dramatic improvement in the performance of the model. So this is interesting. It suggests that the model actually is taking through some reasoning steps to get to the answer, and that a multitude of different alternative approaches to solving the problem is possible, and that if you took those different paths, you would end up with a much more reliable answer. So I think this gives a clue as to how we might be able to understand uncertainty or reliability of these LLMs in the future. Here's a plot that shows how when we use self-consistency added with the chain of thought capabilities into a fairly large language model called PaLM-2, we ended up with 92% accuracy on GSM 8K, which is a standard benchmark for mathematical reasoning. Really impressive improvement on the performance of these models. And then the next thing that we started thinking about was what us computer scientists always love about how to solve problems, which is decomposition, right? You take a very complicated problem that originally would have been very difficult, even through chain of thought prompting, to get the answer because it has too many pieces and too complicated. What you want to do is decompose that complex problem into a subset, a list of subproblems, and then you order those subproblems from the least complex to the most complex, so that it kind of, in a way, in a recursion perhaps, would build up to solve a much larger problem. So an example of this would be something like a math problem, like it takes Amy 4 minutes to climb to the top of a slide, it takes her 1 minute to slide down. The water slide closes in 15 minutes. How many times can she slide before it closes? And if you decompose the problem into two pieces, which would be natural, you say, well, how long does each trip take? And you ask the model to compute that first, and then you ask the question, now how many trips can Amy take? And it gets the answer correct, right? Decomposing the way that we expect your computer science students to do in their first year. For those of you who are professors that are still teaching first year programming classes, right? This is the way that we teach. So it's amazing that we can teach language model the same way that we would teach our freshmen. Now, if you combine all these things into instruction fine-tuning, and as I mentioned earlier, that the way that we thought about machine learning was prediction. We just put in an example and an output, example and a label. And then at test time, we give it an unseen example, an instance, and we ask what's the output is. In instruction fine-tuning, what we try to do is give it instructions, and then say, this is the response. Give it another instruction. This is the so it's a lot more like teaching a kid. Now, instead of an example, you can give it an unseen instruction that is never seen before, and will follow that instruction. So here's an example. Right? Fine-tune the model on a large set of varied instructions so that it can perform a wide variety of tasks using simple and intuitive description of the task. Like, for example, classify this movie as positive or negative. Use this example because in KDD, I believe we may even have KDD cup in trying to do some of these things. Or translate the sentence into Danish, right? So we give these instructions, we give them examples of how the output should look like, and then we fine-tune the model with all these varied instructions. One of the things that we noticed in applying this technique was that in order for it to actually improve performance on unseen tasks, the model has to be of sufficient size and capacity. If it was below a certain size and capacity, the instruction following capability of the model was greatly diminished. Here's a plot on the right-hand side that shows the model size on the x-axis and the performance of the model when it's using instruction fine-tuning. You can see that at a certain point, there's this inflection point where the instruction following capability of the language model dramatically improves. So this seems to be another slightly unexplained phenomenon that's happening in this revolution that we need to get to the bottom of. As a scientist, I'm deeply curious, which you were talking about, like how does humans do this, right? We need to figure out how machines do this as well. Here's a plot that shows how this kind of instruction fine-tuning greatly improves the performance of these models on things like, for example, inference entailment, reading comprehension, or question and answering performance of these models. We followed up the first instruction fine-tuning paper with the second paper called FLAM 2, where we fine-tuned with 1,800 tasks and a much bigger model, and then specifically added in not just instructions, but those explanations that we had talked about under the chain of thought prompting technique. And we, again, saw dramatic improvements in the performance of the model. So in summary, I hope this was a reasonable short kind of overview, tutorial, if you will, of all the things that have been happening in the reasoning space, particularly these 4 ideas, where you use chain of thought prompting to give an explanation, you use self-consistency to ask the model to try various different ways of solving the problem, and then you also teach it the capability of decomposing a problem into smaller pieces and solving each smaller piece sequentially in order to arrive at the final answer, and then giving many of these kinds of examples to the model so that it can perform a wide variety of tasks. This is what's actually powering a lot of the reasoning capabilities of LLMs. And because I only had a short amount of time to give you an overview of this space, Danny is going to be giving a keynote just, I guess, an hour or so from now in the LLM day. So please go to that in Grand A room, where you could get a little bit more detail of the work that's described here. Now, at this point, I would like to turn our attention a little bit to what are some of the future challenges in this space. And this is also, by the way, a clue for you to get your questions ready. We did save some time at the end in case some of you are wondering about what some of these future challenges might look like. But the first one, I think is pretty obvious, is responsibility and safety. And this has been actually one of the most vexing challenges that we had to deal with when we pushed out the Bard prototype. Now, I think it's worth saying that we thank our colleagues at OpenAI for having the courage in pushing out ChatGPT, because that helped our Lambda team to make our case that we also needed to be out there in the market with our capability. But when we think about the Google's AI principle, and many of the other companies have similar principles, how to be socially beneficial, how to avoid or reinforcing unfair bias, or being accountable to people, being transparent, dealing with privacy. These are all super challenges that we have to deal with in LLM. And in many of these areas, we still don't entirely understand how to solve. I don't have slides for this, but one of the things I wanted to mention is it turns out that the reasoning capability, having the instruction capability, was one of the keys in teaching the model how to act in a safe manner. You basically give it instructions, or not just keep giving it negative examples, which would have been the old way in machine learning how to solve this problem, but use a technique nowadays a lot of people in the LLM space would call constitutional AI, where you teach it rules about how to act, just like the way that you would teach kids about how to act in front of adults, for example. So there's some hope in greatly pushing even more capabilities in this space. The second challenge is grounding and attribution of answers. Notice I didn't entirely just say factuality, because for those of you who remember the horrors of taking Philosophy 101 in your college courses, you realize that factuality is actually a deep, long pursuit in philosophy in trying to understand what is a fact and what is not a fact. Right? So grounding and attribution goes to thinking about what is the authoritative sources for thinking about what the nature of a fact really means. And so solving this problem requires attribution to the original source, understanding what the evidence is, and whether those evidences, through reasoning processes, actually entail a particular fact that you're stating, right? So figuring this out also is a key challenge that we're still working on. Another interesting key challenge that people have already started talking about is that these generative AI capabilities obviously are generating content on the web now. So this means that it's quite possible, already happening right now, is that companies like Google and OpenAI and others are already crawling the web that is starting to fill with Bard and ChatGPT and other generative AI cloud answers that then gets fed back into the model. And if those answers were not factual, for example, were not grounded and attributed, then we get this kind of loop of things. By the way, this is how rumor mills and misinformation can start. And so these loops where we want to avoid of using LLM generated example for future LLMs is an unsolved problem. And the reason why it's an unsolved problem is ironic, by the way, is that humans are not good at detecting which answers came from a machine versus some other places. And, from a Turing test point of view, this is deeply ironic, of course, right? Because the fact that we can't detect it means that we're more likely to be training on it in the future. So even having human in the loop is not the answer to the question here. So how are we going to solve this problem is unknown. Another key challenge will be actually personalizing these LLMs. I keep going back to the example of personalized assistant as a vision for some of the things that we want these systems to be able to do in the future. We want the LLM experience to be personalized to you, understand your needs, maybe take care of your coffee, and respect your privacy, right? I guess I prefer lattes. That's not necessarily something that I would worry about other people knowing. But there are other facts about what my interests are that I might not want other people to know. But I'm going to tell that to my personal assistant. And an assistant, a human assistant, is aware of the sensitivities of some of that information. How do we teach that sensitivity to Bard or other LLMs? Unknown. And of course, these models were already expensive. And if we have to personalize it to you, if all the parameters have to change in some way, then serving billions of these compute cycles for you personally, maybe one for Yuri, another one for Yijo, that would be billions and billions of models that all are billions of parameters each that we have to store in the cloud in some way. That's clearly not a feasible future that we want to be in. So how do we use maybe low-rank capabilities or some other efficiency methods to personalize these experiences? Maybe prompting techniques is good enough. We don't know the answer to these questions. People who figure this out, by the way, will easily make a lot of money. So for those of you who are PhD students interested in the future, I would personally invest in this one just for fun. Another one that we have seen in recommendation systems is the pigeonhole problem. Human assistants are very good at understanding what are ephemeral sort of requests that you have. Like, oh, today I feel like a macchiato, or today I feel like a caramelized coffee drink, something sweeter, just because I'm giving a keynote. So, a little bit of sugar doesn't hurt anybody. But I wouldn't want you to memorize this and give me a caramelized macchiato in the future, right? Because my preferred drink is still latte. So avoiding over-memorization of preferences, one of the things that happens with machines is that they're too good at actually memorization in the past. And so we have to figure out what are ephemeral preferences and what are not ephemeral preferences. I just realized last night, I wanted to put this slide back in. There's a reason for this, because I was talking to another conference attendee yesterday, and I realized if you look at this list of responsibility, factuality, and this content loop problem and personalization, many of these problems are actually present in the other half of my team that's working on recommendations. Right? How do you deal with co-star items? How do you deal with personalization and pigeonhole? How do you deal with grounding? And how do you deal with safety? Were all problems that were happening in recommendation systems. And I know many of you work on those systems as well. And so it turns out all the thoughts that you have there in those spaces may indeed be very good solutions to the LLM revolution going forward. So in summary, what has the history told us? Well, every 8 years, we seem to be going through some sort of revolution. And we kind of missed one in 2015 or so. Now it's 8 years later from 2015. We're in 2023, and I think we're right on time. We're right on time for that earthquake. The first applications of LLMs were chatbots because it was natural. It understood context a lot better. So it seemed like it was going to be able to have very natural conversation with you. And that indeed turned out to be the case. There are companies out there that are building characters just for you to chat to because it's a great way to pass some time. But what I think is really amazing about LLMs is that just like how humans are empowered by tools like search engines and reasoning capabilities that are imbued to us the moment that we were born, LLMs are now being augmented by tools, by search engines. And I hope I have demonstrated to you that they are capable of some basic reasoning capabilities through language. And this is an incredible thing to be happening in my lifetime. I never thought when I was going to school, graduate school, that artificial general intelligence might happen in my lifetime. Now I can actually see the light at the end of the tunnel. I think the LLM revolution is still very early in its early stages, and it will revolutionize the way that we interact with AI, and that it will make a significant impact in our lives. We'll all be able to have a personal assistant, and hopefully robots that are also driven by LLMs, so it would actually go and fetch the coffee. And we can all wake up to this revolution, and we can all be part of it. Thank you very much.